Moore's law is dead. So Moore's law, what is that? Basically was the idea that the number of transistors on an integrated circuit would double every 2 years. And it was formulated by this man, Gordon Moore. And this is an idea that kind of was the basis for hardware development for a while. He based it on this graph and this data. And the y-axis there is a log scale. So the linear nature means that it's doubling over some period of time. And that continued up until the present day. And you can see that this trend largely held true and enabled a lot of advances, not only advances in hardware, but the improved performance of these chips enabled us to make a lot of advances in software. But eventually, Moore's law ran into something, a problem. It ran into physics. And I put this up here. This is a representation of the highest level of physics I attained. So this explanation will be brief. But basically, as you're trying to shrink these transistors down and put more and more of them on a chip, you run into some fundamental physical limitations. I think they're down to like 3 nanometer scale now, or they're working on it. And some things just start to get harder. And if you really care about it, I would also look up Dennard scaling. This has to do, so Moore's law is the size of the transistors and how many you can fit. Dennard scaling has to do with the heat coming off of the chip. And so this actually also turns out to be a big issue. Basically, it used to be that you could have basically constant heat off of a given area, but that hasn't held either. And so you get these ideas about the death of Moore's law. People have been writing about it in the last couple of years. The end of Moore, death of Moore's law, a lot of people writing articles, but you still might not be convinced about the death of Moore's law. I mean, it's been true for decades. And so this guy said, I guess I see Moore's law dying pretty soon, maybe in the next decade. And this man is someone I really trust, because this is Gordon Moore, and he said that in 2015. So even the namesake of the law thinks that we're going to start to run into some issues. And so that leads us into the question, then why GPUs? So what is it about these devices that can help us to overcome or at least go around some of these limitations we're facing in the scaling up of our hardware? And so we have to talk a little bit about the history of the GPU. It was originally designed for gaming purposes. So it was designed to be really good at graphics rendering. But it turns out that's pretty useful because a lot of graphics rendering involves operations on matrices, where these matrices might be groups of pixels that you then have to shift or warp. And so that's what the device was originally designed for. And so to understand a little bit more about the GPU and how it compares to the CPU, we can look at 2 recent models. So on the left, this is Nvidia's 2080 Ti. On the right, you've got an Intel i9 processor. And both of these are pretty high-level consumer devices in their respective classes. And so you can start looking at the specs. And the first thing you should notice is comparing core count. And so the CPU has 8 cores or 16 if you enable hyperthreading. And the GPU has 68 of what you call a streaming multiprocessor. And then even more than that, has thousands of what you call CUDA cores. And there's some dispute over, well, is a CUDA core comparable to a CPU core? Some people say it's more fair to compare the streaming multiprocessor. But either way, you can see that the GPU has an advantage in terms of the number of processing units it's able to use at a given time. On the other hand, you can see that the base clock rates are much higher on the CPU, so almost 3 times higher. And so that's where you start to get into the trade-offs of computation on the CPU and the GPU. The GPU might be able to do more things at a time, but it's going to be slower. And so you have to figure out how can we work with that. And so this is kind of a basic diagram of the architecture of CPU versus GPU. And the caption gets to the heart of why we can use the GPU to solve some of these problems. Basically, the GPU devotes more transistors to data processing. And this goes back to the question about Moore's law. So if we can fit like fewer and fewer transistors on the chip, so that direction is not going to help us. We're not able to, or not fewer and fewer, but at least not able to scale as we were before. The question is then, how can we use the transistors that we have in a way that's more efficient for the processing that we need to do? And so the GPU is full of these green blocks in this diagram, and those are basically the units that do the arithmetic, so the floating point operations. And so it's able to devote more of the processing to that. And that's at the expense of some of these things that we've come to appreciate about a CPU as a general purpose computing device. So you can see it has a smaller amount of cache. It has a smaller amount of transistors devoted to control flow. And so these are the things that allow the CPU to be a general processor. And so by sacrificing those and devoting more of the chip to just doing plain arithmetic, the GPU is able to do better in certain workflows. And because of that, you start to see a rise in a trend called GPGPU. So this is general purpose computing on the GPU. And basically, from this paper by Nvidia, it's saying, well, we used to think it could only be good for computer graphics. But now, as we understand it, they can be used for other kinds of parallel processing. And so there's different models that came about kind of in the same time frame. You have CUDA. AMD has their own. There's an open version called OpenCL. But these are trying to accomplish the same thing and basically say, how can we take these devices and use them as parallel processors? And it's one thing I want to point out is this research is just, I think, now starting to really have an impact and be appreciated. This was like 3 or 4 days ago. As I was working on this came up in my Twitter feed. And it's one of these fundamental papers that is basically figuring out how we can do linear algebra on a GPU and had some insights into benchmarking CUDA kernels and how to really get performance out of these devices. And so this just won a Test of Time award. So that's just interesting. And I think we're just now starting to see really the impact of this research. And as the devices improve and as our software tools improve as well. And so in this talk, we're going to answer some fundamental questions. One, why GPUs? We've just gone over this. The second one, you might be wondering, what is CUDA? And we'll get into that question. CUDA in my Python, so how can you, as Python programmers, start to use CUDA in your own programs and to improve your workflows? And then what next? So once you've started to understand a little bit about this, what can you do with it, and how can you continue to move forward if you're interested? So before we get into that, I want to talk a little bit about me, my motivations, why I'm interested in this. So my work, I work as a software engineer at Compass. We're building a real estate platform, and there I work on data pipelines and machine learning projects. And so we're using a bunch of common Python open source tools to accomplish these. So PySpark and Airflow for some of the ETL, and then Jupyter and MXNet for some of the more machine learning data science projects. So to give an example of a project I recently worked on, this is homepage recommendations. We launched this pretty recently. So if you've been on our site looking for different homes, we can take that and display you homes that you might be interested in. A note on this, we haven't started using GPUs yet, but the data that we have comes with rich images and text. And so these are places where I think we're going to need to start to strategize and start to use GPUs in the future. So my real interest in GPUs started with my hobbies, which include deep learning. So I got involved in the FastAI courses. I've basically gone through every session over the last 2 or 3 years, got involved in Kaggle competitions, mostly computer vision ones. Really, really like PyTorch. And so you can see here too, this is my, my home computer. So I've got 2 Nvidia GPUs there. Decided to build my own after one weekend where I was running on the cloud on AWS. I forgot to turn it off. On Monday, hundreds of dollars of bills. And you're like, OK, well, I should spend that on building my own. And that led me to formulate something I like to call Horton's law. You see I've repurposed a diagram from before. It's the doubling of your AWS bill as your interest in deep learning grows. So be careful about that. And last year, another thing that kind of sparked my interest, I made a PR to PyTorch, basically moving a function that had been in the Python side of the library into the C++ side of the library. So basically just padding of tensors. But that gave me some view into the build system of PyTorch and this library of exposing a Python API, but behind the scenes, some of it's in C++, some of it's in CUDA. And so this is what kind of got me thinking about how this all works and how it can be put together. And so, yeah, at the present, right now, what people are using GPUs for, I think a lot of people have heard GPUs for deep learning. So there's all these frameworks, not only PyTorch, TensorFlow, MXNet, Chainer. But this talk is also about what we can use it for. So once we as Python developers understand how to apply this, maybe the future includes GPU databases. And this is something that I think people have been working on, I mean, for years, but this is just one recent example. Uber made AresDB. This is an analytics database powered by GPUs. And another project that I'm really excited about, and even in the last couple months, there's been a lot of progress, is called Rapids from Nvidia. And so their kind of vision is the whole data science, machine learning workflow on GPUs. So not just the modeling side, but also data pre-processing, and then after data visualization. And all these things maybe could be accelerated by using GPU. So, and this is like a very current, like there's a lot of stuff happening. I can't even keep up with it. So this is a really cool project. And this is the kind of thing I think we can do more of as more people understand working with CUDA in Python. So to get to the question that I think you all came here to try to answer, how can you start programming on the GPU? I put together an example. This is a NumPy example. Basically, if you make two really long vectors and add them together. So this is how you would do it in NumPy. And now I'm going to show you how you can do this on the GPU. That's the GPU version. OK, I'll show you again. NumPy version, GPU version. I've highlighted the differences. And I benchmarked it, and just these changes alone can get you up to a 30x speed up. So that's it. You can all go and program on the GPU. Thank you. So that's not the whole answer. We'll talk about different ways that you can use CUDA in your Python programs. One, which I just demonstrated, is a drop-in replacement. So this is kind of level one that I would suggest, is there are libraries that let you just modify a very small amount of your code and try to mimic APIs that you're familiar with. The second one is using Numba. It can do some just-in-time compilation of Python functions into CUDA code. The third one is basically writing a CUDA string and then compiling it in your Python program. And the fourth one is probably the most complex, and that's just writing your own C++ extension to Python. So we'll start with the first one, drop-in replacement. What I had as an example there is CuPy. It's supposed to be a drop-in for NumPy. And there's actually a whole talk about it right after this one. So I'm not going to spend a ton of time describing it. But basically, if you have a NumPy-based workload, you should be able to drop this in. And it supports most of what NumPy does. And it can get you, like I said, some nice speedups just from that. There are some API differences I wanted to highlight. So for data types, the GPUs still aren't very good at working with strings or objects. There's some work being done on that, but right now that's not supported. There's also array creation. So NumPy basically can take a list of NumPy arrays and turn that into a NumPy array. And CuPy doesn't support that. And the last thing is NumPy can return scalar values. So if you do a sum, it's going to return you a scalar value that's the sum. And just because of the way that the GPU processor is set up, it just wants to return you a vector. So that's just going to be a zero-dimension vector instead of a scalar. So those are just a couple of differences, but those are pretty minor. And like I said, if you already have a pretty heavy like NumPy-based code base, you should be able to try this out and see if it can work for you. So there's a couple more CUDA drop-ins, and these are from Rapids. So if you're using pandas, there's now CUDF, which again tries to mimic the API of pandas that people are familiar with. And then they're working on QML, which is a CUDA-powered alternate to scikit-learn. And there's more things being added to that library. Yeah, so that's kind of the drop-in approach. And that's what I would suggest starting with if you're already familiar with some of these PyData tools. So if you're going beyond drop-in approach, you're going to need to start learning about writing CUDA kernels, writing actual CUDA code. And so we should talk about the CUDA API. What is CUDA? How does it work? And the heart of that is the model of threads, blocks, and grids. And so this is a diagram. This is basically how the execution is broken up in a CUDA program between these threads, blocks, and grids. So threads. Threads are the basic unit of execution. A thread is executing CUDA code, and it has a thread index in up to 3 dimensions. This is a really important part, one of the most fundamental parts, I think, to understand about CUDA. So the thread index lets you easily describe what part of the data you want to do work on. And so the question comes, why does this index have 3 dimensions? Like indexes usually maybe 1 dimension, or your arrays and your data might have 2 or 3 dimensions. And so basically the kinds of workloads we're going to be using the GPU for usually have some form of what's called data parallelism. And so that's basically you're taking an operation and you're performing it on different subsets of this data. So say you have a big matrix and you want to add it to another big matrix, different threads are going to be responsible for adding together different parts of that. And then in the end, you'll have the result. So especially a lot of vector and matrix operations can be done in that way. And so this is a basic example. If you've ever written code using threads, you might have had to do something like this where you're saying, okay, I have my data. In this case, this is an array of length 9, and you have 4 threads. And so you're assigning the threads to do work on different slices of the data. And in this 1D example, you can see which thread is supposed to work on different parts of the data. So thread 0 takes 0, 4, and 8. I mean, this is just one way to organize it, right? But you can say 0, 4, and 8, and 1 and 5. And this allows you to write just a logical rule to tell the thread which part of the array it works on, right? So that's your thread index plus the number of threads times I. And so you go through that until you've worked on the whole array. And so that's how you can split up the threads in a 1D case. But the question is, what if your data itself is in 2 dimensions? Then you start having to say, okay, I'm going to use some sort of modulo. I'm going to have to do some division on the length of the different dimensions of the data. And so writing this code can be pretty tricky, getting basically 1-dimensional index of threads into a 2D data set. And the 3D example, I couldn't even really put it together on the slide. And so one of the fundamental insights of CUDA programming is saying, what if you could assign indexes to your threads in the same dimensionality as your data? So you have basically a 2-dimensional array of threads operating on a 2-dimensional array of data. And that allows you to write rules that assign the threads to different parts of the data in a way that's more clear. And you can see that this basically lines up with a diagram from the guide. So these threads are indexed in 2 dimensions. So this thread in the top left is 0, 0, and then 1, 0, and so on. And so this basically lets you match the thread index to the data that you're working on. And so this is kind of how it's organized. So then you get into blocks. And a block is basically just a group of threads. It gives you 2 important features. So one is fast shared memory. So in the device, the GPU, it does have RAM, and like global memory, but then each thread in a block can also operate on memory that is shared and faster to access. So there's a memory hierarchy in the GPU, just like you might see in a normal processor. And so the block gives the threads access to shared memory. And because of that, also needs to be able to perform thread synchronization. So because these threads can access that shared memory, it needs to be able to synchronize them in some basic ways. And so in the same way you can index your threads, you can index your blocks. So block index also has 3 dimensions. And as your data gets more complicated, you may need to use that. And then a grid is just a group of blocks. So you basically have this 3-level hierarchy, threads into blocks, into grids. And that's what this looks like. So that's kind of the basic execution structure of a CUDA program. And it kind of lines up with this GPU architecture diagram where each of your threads is going to be able to execute on one of these green blocks, which is doing some floating point operations. So then, now that we understand kind of the paradigm of working with threads and blocks and grids and how that's kind of laid out, we can talk about what a CUDA kernel, CUDA code looks like. So this is one example. And the first thing to note is this is organized into 2 functions. So you have your main function, and then you have this matrix add function on the top. And to understand this, we should understand basically how CUDA code is executed. It's set up so that some of the code is executed on a CPU, which in the CUDA paradigm is referred to as host, and then some of the code is executed on GPU, which is called device. So if we go back to that, basically the function that's tagged global is going to execute on the device. The main function is going to execute on the CPU as normal. And when that happens, the CPU and GPU are also able to pass data between themselves, and that's kind of the tricky part of getting the programming right. But the CPU is obviously going to handle getting the data in most cases, right? If you load it off of a file system or otherwise have it in memory in your CPU, it's going to transfer that to the GPU, execute CUDA code, and then send the results back. So CUDA kernels are basically just C++ code with a couple extensions. The syntax, this global symbol, like I mentioned, is identifying a function that's going to execute on the GPU device. And then there's these angle bracket syntax that basically identifies the grid size and the block size. So you're able to allocate a number of blocks and those into grids to execute this specific call. So this is just the example again. And you can also see it's making use of some of these things I talked about. So it's using block index and the block dimension and the thread index. So getting into how can we start writing these kernels, the first one I wanted to talk about is basically numba and you doing just-in-time compilation on your CUDA functions. So what is numba? It's a just-in-time compiler. A lot of people are familiar with it for speeding up CPU code. Basically, you decorate a Python function, and when numba sees that, it compiles it into machine code. It uses LLVM, compiles it into machine code, caches that, and is able to call that function. And it executes more quickly, especially if you're calling that function again and again. The compilation step happens once, and then you're able to execute that as needed. And so this is an example on the CPU. So this is doing a logistic regression. And this shows you what kind of code numba is good for. Mostly code that involves numpy and then also maybe for loops is kind of what it's designed to do. And it's designed to speed that up. And it's not just for CPUs. I picked this tutorial. I think this is a good intro to numba, but also I like the title, Tell Those C++ Bullies to Get Lost. But that's mainly what it's used for now is speeding up scientific code that otherwise would need to be rewritten in C++. But it's not just for CPUs. And so you can imagine the same paradigm can be applied to CUDA code where you decorate your function. It just in time compiles that not to machine code for the CPU, but rather to code for your GPU, and then is able to execute that function. And so this is just one example. It's decorated with a CUDA.jit decorator, and then it uses, again, some of these things, thread index and block index, and is able to basically increment everything in this array by one, but in a parallel way. And there are some limitations to this, and not every Python language feature is supported because it has to compile this down into CUDA code, so exception handling, any kind of comprehensions, those are just too complex for the JIT compiler to understand, as well as NumPy features that result in array creation are also not allowed because basically that can be really inefficient to actually allocate that memory on the fly in the function itself. So if you want to have output, you want to pass in an empty array and then have the output stored in there. But there's a lot of useful features. One is access to some of these CUDA features we talked about in your Python functions. There's also CUDA simulator that's cool, and interoperability using this magic method. So basically, on this numba.CUDA module, it gives you access to a lot of the things you need to write CUDA code or CUDA-like code in Python. So it gives you like these thread indexes and block indexes. It gives you a way to sync threads. And these are all things you would have access to if you were writing it in CUDA, kind of C++. But this gives you access to it on the Python module, as well as some CUDA atomic operations that you might find useful. So there's an atomic addition. And these are all made available on the numba.CUDA module. The other cool thing is CUDA simulator. So this could be really useful for testing and debugging. Basically, it simulates the execution in the Python interpreter. So you can actually just, for example, drop a trace inside of this function, and it would let you print things and otherwise debug as you normally would. And so that could be a really killer feature if you're used to that kind of workflow. And the final thing I think is really neat is Numba has kind of started this interoperability using this CUDA array interface. It's inspired by NumPy, which has array interface. But basically, if an array in, say, like PyTorch or CuPy or any of these GPU libraries exposes this information, which is basically the shape of the tensor or the array, the shape, the type, a pointer to it in memory, and then some information about how it's laid out. Basically, you can have zero memory conversion between different libraries, which up to this point wasn't really supported. And this, like I said, CuPy supports it, PyTorch, Rapids. There's some effort to do it in TensorFlow. There's an open issue. But this is pretty cool because I think in the future, people are going to be working across a lot of these different libraries. So the next one I want to talk about is PyCUDA. So this was kind of a scientific project. It's actually described in a research paper. It's one of the first libraries I've encountered that has a whole paper about it. So if you're interested, you can read that. And it's largely applied in scientific contexts. And so this is some example code. And basically, it takes CUDA code that you've written in a string in your Python program and compiles that. And then you can use that function on your arrays. And I know that sounds a little bit weird, but there are some advantages that I want to talk about. So the benefits of PyCUDA, there's a couple things that it gives you. Automatic memory management. So basically, you can use the lifetime of Python objects to be able to deallocate the CUDA memory. There's some nice classes around data transfer. So like I said, you're executing code on the CPU and the GPU and moving data between them. That can get really complicated. So there's some utility classes in PyCUDA called in, out, and in, out that basically say, OK, this data only needs to go in versus obviously out, and in, out does both. And it basically simplifies these steps that you would need to do, which is basically create a CPU array, allocate GPU memory, transfer it, actually do the work, and then transfer it back. And so basically, PyCUDA has some convenience classes that will do that for you. The other thing is automatic error checking. This is from the documentation of CUDA. If an asynchronous error occurs, it will be reported by some subsequent unrelated runtime function call. So that's really fun. CUDA does a lot of things asynchronously, and I guess they decided that this was a sane way to handle errors. Luckily, PyCUDA can check those for you and raises them as Python exceptions. So that's just going to be a lot nicer to deal with. You can also do metaprogramming. I think this is one of the great features of PyCUDA. Basically, a lot of these, there's a lot of parameters you might have to tune to get good performance out of your CUDA kernel. And so, like, for example, how many threads to put in your block and so on. And so with PyCUDA, you can basically experiment with a lot of these and just choose whichever one's fastest. Because it's compiling a string that's in your Python program, you can just use string templating. So this uses Jinja that people might be familiar with. And then you just template in some of these parameters. And so that lets you very quickly iterate on different parameters and do performance tuning in a way that's, I think, much more easy than actually editing the code and doing all that. And for the sake of comparison, I will point out CuPy also has some of this functionality. So you can do what's called a raw kernel. And you can see it looks kind of like what you would see in PyCUDA, where you write your CUDA code as this Python string, and then you can compile it and access it. So that's something to look into if that method appeals to you. So then the last thing to talk about is just building your own C, C++ extension. CUDA is a special syntax of C++, and so this might make sense for you. So the question comes up, why not use C++? Someone asked me this once when I got to this part. It's like, well, OK, why not use C++? And the answer is, I'm speaking at a Python conference, so I have to talk about Python. No, the real answer is because a lot of people already do this. A lot of powerful libraries, not only using GPU, but also CPU, have this paradigm where they basically choose a Python API, but C or C++ performance. And I think that's one of the great things about the language is that you don't have to sacrifice the beauty of the code in order to call into some of these library functions and to access these parts of your system. And so that's why I think this method is still useful and useful even outside of just going into C++ world. So Python lets you do this. It's in the official documentation because at least for CPython, the interpreter is C, so it's not that hard to get this interoperability. I will point out, though, it says it is quite easy to add new built-in modules to Python. And as you'll see, I don't think it's quite that easy, for one, if you know how to program in C. So for people encountering this, like maybe you just know Python, you're like, I'm going to look in the documentation. So if you've already learned how to program in C, maybe it can be quite easy. I think it's a little bit trickier than that, but maybe someone can PR the documentation. Basically, the two main challenges when you're trying to write basically a CUDA extension, which is going to be similar to a C++ extension. One is actually writing and or generating the C++ code. And then the second one, because you're going to want to let other people use this, or even just use it yourself, is you need to package it into some kind of module. And so working with distutils and creating setup.py also can be a little bit tricky. And so there's a really good repo that kind of is a very stripped down version of this. And so these slides will be posted. You can look at this code. And these people, when I first was like researching this, I thought I was going to have to do it all myself and then reinvent the wheel. But thankfully, they've worked out a lot of the kinks. So you can go through, and I'm just going to walk through a couple of the challenges and basically what you should know if you decide to go down this route. So first, how to write your C++ code. This even did not have a very clear answer when I started researching it. The ecosystem is so crowded if you just ask, I want to add C++ to my Python. So you've got a ton of options: Pyrex, Cython, Swig, a lot of these other ones. I don't know how many of them are maintained. And this is just from one site this is from the Cython docs, but they listed all of these and various pros and cons. So that's the first hard part, is just, there's a lot of ways to do this. And people have not necessarily settled on one. So what to choose? I like Cython. So the repo I talked about when I found it, it had Cython example, it had a Swig example. I don't think Swig is bad, but the Swig stuff looked way more complicated to me. So Cython is really cool. I feel like there's two sides of it. Either they're writing a way for C++ developers to get their code into Python, or they're writing a way for Python developers to get some C++ into their code. Personally, I prefer the latter because I mainly write in Python, and that's what Cython feels like. It's also actively maintained, used in a bunch of projects, so SciPy, Spacey, Falcon, and these are across not just machine learning. Falcon is like a web app or way to build your APIs. If you want to learn more about this, there's a good blog post, Cython, PyBay 11, CFFI, which tool should you use. So those weren't even in the list I put on the last one, so the ecosystem is even bigger, I guess. It's growing. But to give you an example of some Cython code, if you just kind of glance at it, it looks mostly like Python. There's these weird C defs in it that let you specify types. But for the most part, it feels like writing a Python class. And then basically, Cython's going to generate the necessary C++ code out of this file. And so I've been talking a lot about kind of generically creating C++ extensions, but you also need to know, how do I get my CUDA into C++, or how do I compile it? And Nvidia has this NVCC compiler. It basically takes your CUDA code and it compiles the kernel down to GPU assembly, and it also takes out some of these special syntaxes in your host code, replaces those. And it also, you could use your normal C++ compiler to do the CPU code and just use NVCC for the GPU code. And we'll see an example of that. So then we get to, how do you even build it and package it, make sure everything compiles and is included. So this is from the docs on describing extension modules. And here you will see they do at least admit that this could be a bit more complicated. And so this is basically talking about, OK, you use distutils, and you need to have included source files and linking and things you don't have to worry about with Python. And so this is just one example, again, from this repo I mentioned, of how you kind of write this extension most of the code has to do with what should be included. So you're including CUDA system libraries, the source files, but then there's also this weird bit, and it's like, well, how do I use NVCC? I'm just going to put the doc string up there because I read this doc string and I was terrified. I hope this does not convince you not to do this because I think it's useful, but inject deep into dist utils to customize how the dispatch to GCC/NVCC works. So this can get a little bit hairy because it wasn't, Python setup.py wasn't necessarily built to be able to do this and call different compilers on different source files, basically is the fundamental problem. But this can be really useful. And I will say at least this is not as crazy as going into, say, like PyTorch or TensorFlow and figuring out how that's built, because that's like even crazier. So you might be wondering after all of that, like why would you want to do this? But there are a lot of advantages, I think. One is just fewer dependencies, right? Especially if like your core competency if you want that to be like shipping this GPU acceleration, maybe you don't want to depend on CuPy, maybe you don't want to depend on PyCUDA, or have your users have to import a certain version of that and deal with all that. So this is the closest you can get to basically saying, I'm writing raw CUDA over here, I'm writing a Python module here, I'm going to put it together and send that to you, and you can use it. So that's, I think, a really big benefit. The other thing is manual memory management. You might see this as a pro or con, but the fact is that, and this is pretty horrible, and you have to check all the errors too, because you never know when the error is going to come up. It's asynchronous. It looks like Go almost, and you have to do free and malloc. But there's a lot of like kind of specialized CUDA memory things you can do. So mapped memory is something people use a lot. Portable memory, you can look in the docs about these, but you might, as your use case gets more advanced, find yourself having to use these. And even though there's some ways to do these in the high-level libraries, like you're going to get the most control over your memory, as always, if you drop down into like C++ or CUDA. And then the other thing, this is, again, maybe controversial, but a compiler, especially since you're working in CUDA, it might be nice to have a compiler that tells you what went wrong and exactly where it went wrong. I found that pretty useful when I was having to write the CUDA code. So to wrap this all up, how can you get started? So now that you know about these libraries, you might be interested in applying it to your workflows or learning more. First of all, accessing a GPU. So the good news is there's a lot of ways to do this for free now. So Google Colab, Kaggle Kernels are two different ways that give you some access to GPUs for free. Even cloud GPU instances, the prices keep going down. AWS is under $1 an hour. Google Cloud, 50 cents an hour for the GPU. There's some, I think you also have to get a different device and they build differently. There's a parallel programming / CUDA course on Udacity. Here's the links and my slides will be up later. Careful, it was last updated in 2015 and I spent a whole weekend just trying to install OpenCV and have that work. So that might not be so fun, but it's really good material. The videos are great, and if you can get the code working, there's some really good homework to work through. There was recently a Rapids tutorial at SciPy. I actually haven't had a chance to watch it, but I watched like the first 10 minutes, and like I said, I think this is a super cool project, so learning more about it I think would be beneficial. And then basically what can you do? I think one, start applying CUDA to your workflow, maybe with some drop-ins, maybe other things. Start learning about parallel programming algorithms and things you can do with those. And then the last thing I will say, it's kind of more future-looking, is there might be other kinds of devices. They're already talking about kind of XPU architecture, so not just GPU, but also TPU, maybe even FPGA, and there's ways to do that through Python. And so if you're really interested in the hardware side of it, there's a kind of a long rabbit hole you can go down there. And no matter what you do, I will tell you, always remember Horton's law. Be careful. That's it. Now you can go program the GPU.
Okay, thank you so much, William. We have a couple of minutes for questions. Is there any questions?
This question might be more related to deployments, but I'm aware of that when you go to build or pip install TensorFlow, you get different performance characteristics whether you build it on the host directly that you're targeting, or using like an already pre-built wheel from PyPI. I was kind of curious about the portability of using CuPy code and things like this with Numba, if you have to do anything specific to get the fastest performance possible on a host, and how you might be able to tackle that if you're distributing to multiple different machines with different GPU versions or different CPU versions.
Yeah, that's a good question. And I talked a little bit about the Udacity course, but that is one thing I ran into when trying to get the code from like 2015 to work, is the compiler args to NVCC like change, and like when the architecture changes, it might not be compatible. So I guess that's to say there can be incompatibilities, but I will say like most of the time you should just try to run it like on an updated version of CUDA, and I'm not sure you'll like run into a case where you can't do that, right? In terms of like the different like actual devices, you're going to be fine if you're running it on like a 1080 Ti, 2080 Ti, V100. Like there isn't really much difference there, so you should be okay.
My question was, did any of these alternatives have support for multiple GPUs?
Yeah, that's a good question. I'm trying to remember. I'm pretty sure that CuPy, you can do it. The other ones, I'm not sure. That's not really something I looked into. Sorry.
Any question? Okay.
So when you use that in-out function, it looked like there was an immediate input-output at the end of the application of the kernel, right? Mm-hmm. And I was wondering if you wanted to compose multiple things, you're writing your library of, you have a sum of vectors and then you have a subtraction, and you don't want to take the results of the sum out into memory. You want to keep it in the GPU and have longer stretches of GPU-only computation. How difficult is that? Is that automatic?
Yeah, that's a good question. So I was talking here, I talked about like kernels, and you tag those with like the global, but there is like device functions that you can write that basically exist to only execute on the device itself. And so to do what you'd want to do, you'd want to like compose device functions and have those wrapped in one like kernel, if that makes sense. So you'd want to do one transfer. You could like compose it into multiple functions and then have just one transfer at the end. That's doable, yeah. That's the device function, I think, is right.
Just do individual device functions.
Yeah.
And then delay the wrapping at the later.
Exactly, yeah.
Okay, any more questions? Okay, that's it. Thank you so much, William, for your presentation.